Yeah, it's our great pleasure to as a Michael. Right? Okay, thank you. So yeah, this is our great pleasure to have like Dr. Lucas Tirpitz to join us and give us a seminar. Actually, Lucas is got his PhD from the university in Heidelberg, Germany, and where he developed in situ instruments for ground-based and airborne measurements of volcano emissions. And he also worked on the remote sensing methods, including the topic will be presented in this seminar. And he also, after his PhD, he joined as a research scientist at a company called Aerosols GmbH, and developing commercial spectroscopy instrumentation. So actually, since last year, he was affiliated with UCLA, and where he is investigating radial transfer modeling in wildfire plumes. And it's our great pleasure. Actually, this seminar is actually supported by both Caviar Affinity Group, ASIC, and also he is also invited by the North Star Beers Group. And I also want Dr. Chen Yansao to give a few remarks.
So it's really a great pleasure to have Lucas here. And the history was this. So I was looking for some, ground-based validation capabilities. And that's where I found the instrument called the MAX-DOAS, differential absorption optical spectroscopy. So it just happens I was thinking, maybe a instrument can also add some polarization capabilities. So, nowadays you do a, Google search, and his dissertation came out. So I was, with great interest, I read his dissertation, and that's just right for me. So it was a perfect match almost. And so basically, so in his dissertation, he developed this instrument called the MAX-DOAS, and you scan the sky, and so you got the atmospheric composition, but also he studied the polarization, and so that's a perfect fit for validation because typically you have just a one-point measurement, but here you have an aerial measurement of the sky, so and also the profile. So that's where we interchanged ideas, and actually that led us to develop the mini instrument we call portable DOAS, and we actually deployed it for the NASA flight campaign recently in February and collecting data. So all thanks to him for a lot of the technical exchange and in terms of building the instrument. And certainly polarization is very important, and we are actually facing some issues with the NOAA 20 WIRS instrument because of polarization sensitivity. In addition, there is also the recently launched PACE mission actually has a polarimeter on board. So all of those are connected. And finally, I want to say he's also a radio transfer expert. And as some of you know, that UCLA actually is very well known for radio transfer models. And in particular, the Wheeler-Dot radio transfer model. I know many years ago, we had an initiative to work on this, but it didn't quite work out. I think here is another great opportunity to collaborate with him on the Wheeler-Dot radio transfer model. So because of all of these, exciting areas, and so we invite him to give a seminar, and the rest is up to you to tell us. the details. Thank you very much.
Yeah, thanks a lot for the introduction, and a special thanks also for just having me here and inviting me, especially to Changyong Chao and Xi Xiao. It's a big thing for me and an honor to be here and be able to speak and yeah, and work with you guys for a few days. Yes, I'm a bit a friend of short titles and presentations, but this time I thought, okay, maybe the title was a bit too general. So at least in the slides here, I added at the end with MAX-DOAS. MAX-DOAS is the measurement technique that Changyong Chao was just talking about already. And most of the talk will wrap around this technique here. I will introduce it in a minute. Just as an introduction, the title picture here, this is an all sky image of the sky and taken with a polarizing filter in front of the camera that only transmits the horizontal direction. You can see the sun is just above the horizon, and if you look into the sky at about 90 degrees with respect to the incoming radiation, then molecular scattering polarizes the light in the vertical direction and the sky appears pretty dark. That's a feature that many people know from skylight polarization, but in the details, there's a lot more going on. In fact, the polarization of skylight can tell us some things about atmospheric aerosols and trace gases, and that's what this talk is about, as the title says. After a short introduction, the rest of the talk will be subdivided in three major sections. In the first one, I will introduce the MAX-DOAS measurement technique. The long name is, by the way, multi-axis differential optical absorption spectroscopy, but just forget about it. MAX-DOAS is the word to remember. And MAX-DOAS is a meanwhile well-established ground-based remote sensing technique, and it takes spectra of the skylight in different directions to infer information on atmospheric aerosol and trace gases. And I introduced this technique because most of the talk will be about it. And actually, what was part of my PhD was to enhance MAX-DOAS by polarization measurements, so it becomes polarimetric MAX-DOAS, and to investigate what the use of polarization is for MAX-DOAS in terms of performance and accuracy. And the second section is maybe most interesting for the broader audience. There I will just outline general properties of skylight polarization, which I find very interesting. So as a general motivation, why are we even studying aerosols and trace gases? Of course, we want to understand atmospheric chemistry, like heterogeneous, homogeneous chemistry, particle, cloud interactions, and the like. And we also want some, it's also for monitoring purposes, monitoring air quality, finding areas of high pollution or like. Why is MAX-DOAS a very interesting technique in this context? As a ground-based technique, it's very cost-efficient, simple, and scalable, at least compared to like in situ airborne measurements, as this little graphic illustrates. Yeah, and then there's another point that Changyong already mentioned. It's that MAX-DOAS averages over spatial scales of several kilometers. And this is actually what satellite also do. And so we have, with MAX-DOAS measurements, very representative observations for satellite validation. But so far, the technique also has a lot of limitations to date. So these limitations are being pushed by the community. And yeah, adding polarization was one of the attempts to improve them. Okay, of course, polarimetric remote sensing is nothing new really. We have for decades already now satellites that use polarization like POLDA, MODIS, and most recently the PACE mission, which has these two polarimetric spectrometers on board, which are shown here. LiDARs also use polarimetric information to distinguish different aerosol types. And then there are various ground-based approaches which are passive, so use direct or scattered sunlight. Most prominent is probably the AeroNet network with its sun photometers. And the MAX-DOAS technique is also a ground-based passive technique, but it comes from a bit of a different direction. It measures in a smaller and other spectral range, so it measures in the UV visible. It has a higher resolution because it's originally for trace gas measurements and less for aerosols. And yeah, It also is, it is not radiometrically calibrated, typically, the instruments. So there are different new aspects, and this was the reason why we wanted to investigate polarization specifically for the MAX-DOAS technique. So let's start with part one, the MAX-DOAS technique. How does it even work? You see here on the left side, a typical MAX-DOAS instrument. You have a telescope with 1 to 2 motorized axes and a very narrow field of view. So you can gather light from very distinct directions in the sky. Then the light is guided into a spectrometer unit where it is analyzed. And of course, you have some computer to control the instrument and do the evaluation. And the spectral range that we're dealing with, just to give you an impression, this is a solar spectrum. And MAX-DOAS typically measures between 300 and 500 nanometers. So this is a typical MAX-DOAS skylight spectrum that you record. Now, if we look into the sky, as sketched here, in this direction, for instance, so at a very shallow viewing elevation angle, just a shallow angle above the horizon, what we actually observe is light that comes from the sun, travels through the atmosphere, and gets scattered on aerosols or molecules into our instrument field of view. To be honest, we have a superposition of a bunch of light paths, of course. We have photons that are multiply scattered and ending up in the instrument, or scattered on other points along the line of sight, or even bouncing off the ground. But for qualitative understanding, this is approximately what happens for now. And yeah, it's enough. So on the way, the light interacts with the atmosphere, of course. So the light gets attenuated, for instance, by absorption on aerosols and trace gases. And you also have scattering on aerosol and molecules. And scattering is a bit crazy because it, on the one hand, it attenuates the light by scattering light out of the path. On the other hand, it ensures that any light reaches the instrument at all. It's a bit tricky, but that's just a side comment. The most important question is, can we disentangle these effects? And this is what the DOAS spectral analysis does. And I will explain it in short. So just imagine we have some solar spectrum with intensity I0, dependence of wavelength lambda. In this case, for example, it looks like this. It's smooth in this case for simplicity. And then down with our instrument, we measure some spectrum that underwent some attenuation processes as mentioned here. Now, if we divide these spectra by each other and take the logarithm, we obtain what is called the optical thickness. I guess this is a concept that is quite familiar to most of you. It's just a convenient measure for the attenuation of the light from when it travels from the sun to the instrument. And the nice thing about all these gray effects here in this graphic is, like scattering and aerosol absorption, is that they only alter the broadband shape of the spectrum. So also the optical thickness, if we had only those effects, would still be some smooth curve, so smooth with wavelength as indicated here. This is very different than for the absorption of trace gases. Here are absorption cross-sections for various trace gases that absorb in the UV visible or plotted over wavelength. And you see all this absorption has very characteristic narrowband absorption structures. So if we have one of those gases in our atmosphere, the optical thickness gets additional features which look like this. And thanks to the very different absorption of these gases and to the different behavior of these processes here, the absorption features of each trace gas can be isolated from the rest of the spectroscopic features in the optical thickness. And the magnitude of the spectral signature of each gas is proportional to the slant column density, the SED, which is just the total amount of gas that the light sees along its path through the atmosphere. So it's just the integral of the gas concentration over the light path. And that's an important quantity. Slant column density, SED, remember it for the rest of the talk. Then there's one problem that I would like to point out. Typically, the solar spectrum is not accurately known, and we cannot really measure it with our instrument because we cannot easily remove the atmosphere. So what people do instead, we point the instrument to the zenith, thereby provoking a very short light path through the atmosphere, and then performing the evaluation on the former slide on those two spectra. And then we no longer get the total, the absolute slant column density along this light path, but we get the differential slant column density, which is just the excess gas along the long light path compared to the short one. So differential slant column density, it's not that important for the rest of the talk or for the qualitative understanding, but DSCD is what you always hear in the context, what you always hear in the context of MAX-DOAS measurements, and this is why I want to point it out. For now, just remember it's somehow a measure for the integrated gas amount along the light path. We have two questions left now. The first one is, how do we get information on the light path? And the second question is, where do we get aerosol information from? And it turns out that this is one and the same question because the aerosol content of the atmosphere determines our radiative transfer in the atmosphere. And this can be easily illustrated here. Consider we have little aerosol in the atmosphere, then we have good visibility, then we can see far, and so can our instrument, and we have a long light path. On the other hand, if we have lots of aerosol, visibility is bad, and we get a short light path. So how do we get this kind of information? This is done by taking a proxy gas with a known concentration and measuring that with our method. And in the UV visible, this is the oxygen collision complex, O4. And its concentration is well known because it's just proportional to the square of the oxygen concentration squared. So remember, O4 in the MAX-DOAS world is our proxy for light path and aerosol information. This can be illustrated on this nice plot here from it's saying from a paper. I forgot the reference. Okay, I need to put it. Excuse me. Okay, yeah, anyway, the O4 DSCD is plotted here over the aerosol load in the atmosphere. And you see if you have no aerosol, you have, of course, the long light path. So the light travels through a lot of O4 in the atmosphere, and you get a large O4 DSCD. On the other hand, if we have more aerosol, we have this short light path, as indicated before, short light path through O4 gas, and so we get a small DSCD. And this is how we get our information. Now we have this DSCDs, this differential slant column densities, which are somehow light path integrated concentrations, but they are not really intuitive. What you actually want to end up with is maybe concentrations of aerosols and trace gases. And for that, we use inverse modeling or so-called profile retrievals. Let's repeat what we do during our measurements. What people typically do is they perform elevation scans. So they take the instrument and just change the viewing elevation above the horizon. Thereby, we get different light paths through the atmosphere, for which we can do the spectral evaluation, then get the integrated gas amounts along all these light paths. And yeah, it reminds me of a kind of tomography of the atmosphere, because you can see through the different light paths, we get actual information on the spatial distribution of the gases. But how do we extract them? We do this by setting up an artificial atmosphere in a radiative transport model that knows about all the physics of the photon-atmosphere interactions. In this model, we set up an aerosol concentration profile, trace gas concentration profile, and other parameters. And then in this atmosphere, we simulate our measurements, and then we simply fit this model to the measurements by changing these parameters. And when we brought them into agreement, we say, okay, that's approximately the profiles that we actually had. And for that, for people who are into inversion and remote sensing, we use optimal estimation, just that you know what kind of algorithm we use. So the summary of this first section of the talk is MAX-DOAS works like that. We have the Skylight spectra. We have a spectral analysis that gives us integrated information along the light path, the gas differential stand column densities, where the DSCDs of 04 are our proxy for light path and aerosol. And then we apply inverse modeling to come from this, to get from this integrated quantities to actual gas concentration profiles, aerosol profiles, and so on. This is some example data recorded during a campaign in the Netherlands, where lots of MAX-DOAS instruments were operated in parallel. So this is data for 2 days. These are aerosol profiles. This is altitude here. This is the time of the day. And the color is basically the aerosol load, or the extinction in this case. We have NO2 concentration profiles and formaldehyde concentration profiles. And I think it looks pretty nice, but if you have a closer look, the vertical distribution, for instance, is pretty limited. And in fact, for the remote sensors among you, I show some averaging kernels and degrees of freedom of signal, the so-called DOFs. Both averaging kernels and DOFs are a measure for the information that was actually inferred from the measurements. And yeah, if you can see here that for the lowest layer, we get really good information, like 80 to 90%. But then as you go higher in the atmosphere, the information drops rapidly. And also the vertical resolution of the retrieval, which is indicated by these curves here, is reduced strongly. And this is also why all the profiles are smoothed out on the upper end here. And the degrees of freedom of signal in this case here indicate the number of individual layers that we can actually resolve. And this is really poor, to be honest. I mean, we can 2 to 3 layers. This is what we can actually separate in the atmosphere. And this is why people want to improve the technique. And one of the major questions was then, can polarization improve this? And what we need to do to introduce polarization in this technique is, on the one hand, on the measurement side, we just need to put a polarizing filter, a motorized one, in front of the telescope. We will see later why this works. A linear polarizer, by the way. And on the modeling side, or on the inversion side, we just have to implement the model capability to simulate polarimetric observations. And this is also what we did, and I will show results in the third section of the talk. But for now, I will just outline a few general properties of skylight polarization. This also helps to understand why we would even expect polarization to improve the information content. I want to start with some simple basics on polarization of atmospheric or of skylight. Sunlight arriving at the Earth, top of the atmosphere, is initially unpolarized. So if you have radiation coming towards you, the electromagnetic field vector just oscillates in random directions. And the polarization is then caused in the atmosphere by scattering, mostly molecular Rayleigh scattering, as many know, and also by air scattering on aerosols. And you can end up with different polarization states between partially polarized, where photons of a distinct polarization prevail, or fully polarized light. And what is also important to note is that circular polarization is negligible in the atmosphere, or it is really small. And this makes things a bit easier because like that, we can describe our radiation field by 3 parameters, which are the intensity, then the degree of linear polarization, or DOLP. And yeah, here's the definition, but it's easiest to remember for now. It's 0 for unpolarized light, it's 1 for fully polarized light, and it's something in between for partially polarized light. And then we also need the angle of linear polarization, which just indicates the direction of the prevailing electromagnetic field vector. And because we only have 3 parameters to measure, you can actually get all the information on the radiation field by just putting the polarizer in front of your telescope and drive it to 3 positions, typically 60 degrees apart. Yeah, and I want to highlight the degree of linear polarization again, because this is a quantity that we will look at on the following slides quite a lot. As I said, a number between 0 and 1 just saying how much the light is polarized. How is polarization in the atmosphere actually emerging? Most well-known, molecular scattering or Rayleigh scattering is highly polarizing. If we have light which is unpolarized, so it has a component perpendicular and parallel to the scattering plane, so to the sketch plane here, and it's scattered on molecules, then we have Rayleigh scattering, which has this scattering phase function. In dashed, you have the phase function for the perpendicular polarization, which is isotropic. In contrast, for the parallel polarization, we have this 8 here, and this results in the end in fully polarized light at scattering angles of 90 degrees. And this is, of course, also what we have seen on the title slide. The light comes in here, is unpolarized, then gets scattered, as shown here, and then we have vertical polarization. And if we have a polarizing filter like this, the sky appears black. Then I want to show this plot here, just because on the next slide I will show similar plots of this kind. This is the same phase function as the one here, just not as a polar plot. So you can see this is like the dotted line is for the parallel polarization, gets 0 at 90 degrees and so on. And the new thing here that I put into this plot also this what I call here for simplicity the signed doll degree of linear polarization. The gray curve, it just indicates the degree of polarization that you end up with after a single scattering event. And it's -1 if you end up with perpendicular polarization, and it's +1 if you end up with parallel polarization. And these are now the plots for scattering on aerosols. I put the Rayleigh scattering phase function up here for reference. So first we look at monodisperse aerosols, so aerosols from one size and property. And you see for small particles, we get very similar scattering phase function as for Rayleigh scattering. Please note there's a logarithmic scale here now. Then for the larger the particles get, the more fancy the scattering functions become. And especially the degree, the signed degree of linear polarization in gray, it really jumps up and down and it gets really high magnitudes and yeah, changes sign and all that. So we might expect very different polarization patterns from aerosol. In fact, in the atmosphere, we don't have monodisperse aerosol of a single size, but we have some mixture. So for a typical aerosol size distribution, the phase function actually looks like this, which is more or less a smoothed version or a combined smooth versions of the aerosol of different sizes. And you see that especially the signed degree of linear polarization, the magnitude is decreased, and the pattern is still, the magnitude is still significant, and it's different from the Rayleigh scattering thing. So if you then take a radiative transport model and you can just simulate the angular patterns, so more or less all sky images of the skylight polarization. This is for a pure Rayleigh atmosphere. You see the color is the degree of linear polarization and the white dashes indicate the direction. And this is more or less a simulation of the title picture. You see at 90 degrees to the sun, we have the largest degree of linear polarization. And the features are as you would expect. There are some surprises, like for instance, the horizontal orientation here below the sun. This is due to multiple scattering, but mostly this is what people know. And you can do the similar simulation for an atmosphere that only consists the aerosol mixture that I've shown on the slide before. And on the first glance, the pattern does not change much. The most notable change is that the degree of linear polarization is strongly reduced. But we can measure polarization states in the sky with pretty high accuracy. And then even small changes in the patterns carry quite significant information on the aerosol amount. You get features like this or different directions in the aerosol, in the polarization and so on. And Claudia Emde, for instance, already 2012 did simulations for more aerosols. And you see that the pattern can be very different depending on the kind of aerosol that you have in the atmosphere. So the main take-home message from this slide is that aerosol impacts the angular polarization pattern in the sky. And so this was the angular dimension or the spatial dimension. We can also look at the spectral dimension. And for this purpose, I show two measurements here performed with a polarimetric instrument looking quite close to the horizon. On both days, we took measurements on the same time of day, so under the same viewing geometry, but the conditions in terms of aerosol properties and things were very different for the 2 days. And this is now the degree of linear polarization plotted over wavelength. And there are some features which are quite interesting, I think, to explain. The first one is, in general, towards the UV, the polarization decreases, and towards the vis, it first increases, then it decreases again for very long light paths. And the decrease towards the UV is because multiple scattering gains significance, which and multiple scattered light, at least in this viewing geometry, is less polarized than the single scattered light, and so the polarization decreases. Then we see between the 2 days, we see a big difference in degree of linear polarization, which is related to the amount of aerosol, the properties, and the vertical distribution. So here are the aerosol size distributions for the 2 days, and the aerosol optical thickness changes. On the second day, we have a higher one, and we have more fine aerosol. But I think we also have a very different vertical distribution, which is not shown here, which also improves or strengthens this effect. But you see that the broadband shape really changes a lot. Then we also have narrowband absorption features, which I also find interesting. This is mostly from inelastic light scattering. So inelastic scattering shifts the wavelength of the photons, and it is also strongly depolarizing. So what happens through inelastic scattering is that the solar Fraunhofer lines are basically filled up with unpolarized radiation. And this is why the degree of linear polarization is decreased in solar Fraunhofer lines. And another narrowband absorption features can also be introduced by gas absorption. In the UV, this is, for instance, a strong absorption by ozone, which favors shorter light paths, which in this scenario corresponds to single scattering. And this is why suddenly the degree of polarization goes up again towards the deep UV. Okay, main take-home message from this slide is more or less the spectral patterns can be changed by aerosol and gases, which is good. So we get information on both, hopefully. And then there's this third aspect of polarization that I find very interesting as well. That's if you take measurements at different polarizer orientations, you provoke different light paths through the atmosphere. Basically, with one polarization direction, you turn off single scattering. You can put it like that. And you can simulate this change in light path for different polarizer orientations by simulating the change in the O4 DSCD. You remember the O4 DSCDs in the MAX-DOAS world are our proxy for the light path. And you look into one direction of the sky, you turn the polarizer, and you see how much the O4 DSCD changes. And then you see that it's up to 60% indivisible. And this is a very interesting point because for the MAX-DOAS technique, for our tomography, we are dependent on a lot of different light paths, ideally. And with polarization, we can access new light paths, which hopefully increases our information on aerosols and trace gases at once. So the summary of this second section is basically, we have these three property groups, I put it like that, of the polarization, the angular pattern, which tells us much about aerosol. The spectral patterns tell us about aerosol and trace gases, and the additional light path hopefully also increase our information on both species. Yes, so this, I'm coming to the measurements and results. I ended the second section with this slide. Just to remind you, on the measurement side, we need a motorized polarizer. On the model side, we need to model the polarimetric measurements. And this is what we did. So we built this polarimetric MAX-DOAS instrument, or P-MAX-DOAS. It was a bit of an overkill in the end, maybe, but the most important thing is just this polarizer in the telescope that allows us to record polarimetric information. And then on the model side, we developed a polarimetric MAX-DOAS inversion algorithm called Rhapsody. And here's a table with the main new features that it has compared to conventional MAX-DOAS algorithms. Of course, we can consider the polarization. Then it has a new aerosol model. Conventional algorithms typically used optical simplifications, approximations, like the Hennier-Greenstein approach. And Rhapsody now has a me model, which was necessary to actually reproduce the Skylight polarization patterns accurately. Then the retrieval of aerosol properties is not common practice in the MAX-DOAS conventional world. With Rhapsody, we can now retrieve the microphysical properties from the me model, which are a bimodal size distribution that we assume, defined by two modal radii, two modal width, a modal fraction, and the complex refractive indices of the aerosol material. So in total, 9 parameters. And the last feature that we also implemented and needed was conventional MAX-DOAS algorithm typically only use the information from one wavelength band. And Rhapsody now allows to use the information from multiple wavelength bands. But that's a technical detail, more or less. Then we performed real measurements with the instrument at the Hohenpeißenberg in southern Germany. This is an observatory of the German Weather Service on a hill with a tower and a nice balcony where we put the MAX-DOAS on, and it was looking to the northwest. And we also had some other measurements for validation purposes nearby, in situ instruments for various gases, a sun photometer, Aeronet sun photometer on the house here to measure aerosol optical thicknesses and aerosol properties. And then we also had a LiDAR, or what is called a ceilometer, measuring actual backscatter profiles of aerosols. This is the view from the balcony, just to give you an impression. And you already see what might be problematic. The ground elevation changes quite strongly, and also the surface albedo. So yeah, just to show you this. And then you can do the evaluation. We first did a conventional MAX-DOAS evaluation of the data. So this is data for 3 days for aerosol, formaldehyde, and NO2. And the first row is the ceilometer data, so this LiDAR, the aerosol profiles. They are already smoothed down to the PMAX-DOAS resolution. Then here are the MAX-DOAS retrieved aerosol profiles. And down here we compare the aerosol optical thickness in orange retrieved by the MAX-DOAS, in black from the sun photometer. Then we have formaldehyde profiles for which we don't have validation data, NO2 profiles. And for the NO2, we can compare to the in situ measured NO2 concentration. Yeah, and you see the agreement is it's okay, but it's not that great. To be honest, this difference here is mostly because the MAX-DOAS, it measures actually high concentrations as it just puts them below the in situ sensor, so in the lower layers, as you can see here. The white dashed line, by the way, is the altitude at which the instrument is located. I forgot to tell. So what the question is now, what happens if we add polarimetric information? And what you see is the degrees of freedom of signal are also indicated here, and they go up, especially for the aerosol profiles. I would also say that the agreement improves a little bit for the aerosol profile, but the rest remains. And the aerosol optical thickness. That's very nice to see that it seems like we get more sensitive, especially to the higher altitudes. And so most of the aerosol optical thickness is actually measured. And you can do the same plots, comparison plots for the aerosol properties, but this looks really messy. So what you have here, the same 3 days, and then the aerosol size distribution parameters and the refractive indices. And the first thing that you see with the conventional algorithm, you don't get any information on some of the parameters. And for those who are into optimal estimation, the PMAX-DOAS just stick to the a priori values, which are indicated in gray here, and don't do anything. And there where we get some information, the agreement is not very good. And if we add polarization, we get much more information on these parameters, but the agreement improves between sun photometer and MAX-DOAS, but it's not very convincing, to be honest. And it's really hard to tell what's going on because there are various factors. The validation data, for instance, from the sun photometer here, in black, it's questionable because if you apply recommended quality filtering, they basically all disappear. They get flagged. Then there's on the other hand, we have measurements and parameters where the PMAX-DOAS shows very unphysical values, as you can see down here for the imaginary refractive index. So it's not clear where the errors really come from. Oops. Excuse me. Oh. Yeah, okay.
Hello.
Okay, thanks. And then there's a question about the representative and the comparability of the measurements because they sample different air masses. Then we had this complex terrain and some model assumption might have been too simple. In the end, we decided to just stick to synthetic studies for now to quantify the value of polarization in theory for the MAX-DOAS method. So what we did then was we took a lot of different aerosol profiles and gas profiles, different aerosol properties and different viewing geometries, also including something different than a normal elevation scan. We also used an Almukanta scan, which is just looking at the sun and then turning the azimuth angle of the instrument. And this is what Aeronet instruments, for instance, do, but thereby get a lot of information on the scattering phase function of the aerosol. So we put all these scenarios into our model and simulated measurements for approximately 1,000 scenarios in total. And then we performed retrievals on the basis of this data and saw how well we can reproduce the actual input data. And then we can, of course, remove and add observations that we put into our retrieval and see how the information content changes. And we can do this in a very controlled manner compared to the real measurements. Yeah. And this is the results. So this is the information content analysis in terms of degrees of freedom of signal again. So what you see here is histograms of the degrees of freedom of signal for different parameter subgroups, for aerosol profile in blue, for trace gas profiles in orange, and here for this dotted histograms indicate the degrees of freedom for the aerosol properties. The thick lines are just the average values of each histogram. Okay, and the histograms are just the different scenarios. Yeah. And this is for the conventional retrieval. And then if we activate the feature that I mentioned a few slides before, that we use information from different wavelengths first, the situation already improves. We get the DOFs slightly increase for all, especially for the aerosol properties. Now, most important, if we add polarization to our retrieval, we see a significant increase for all the aerosol-related properties, especially for fine mode aerosol, but also aerosol profiles. At least the relative increase is pretty strong, and also for the coarse mode aerosols, but also on the aerosol on the surface albedo. And unfortunately, not that much on the trace gases. So this is one of the main new aspects, how much information we can actually get from polarization on the trace gases. And yeah, it's a bit sad to see that it's not of such a great value, but it helps at least a bit. If you also add an Almukanta scan to our retrieval, the aerosol property, the information even increases. And you see we end up with very high information on the fine mode of the aerosol properties. Less on the coarse mode, but also on aerosol profile. And also the modal fraction gets high up. Yeah. But the most important thing from this slide is this increase by introducing polarization. Yeah. And to finish, I also show some retrieval results actually. This is the profiles that we put in. So this is also for the synthetic data still. We have aerosol profiles from aldehyde and NO2. Then we have the size distribution parameters, refractive indices, and so on. And the surface albedo, that's a very busy plot. But in the end, if orange, the retrieved value, and the green values match up, everything is great and we're happy. And otherwise, it's not that good. And this is for the conventional retrieval. And you see that the aerosol profile cannot really be retrieved well. And also the parameters are mostly very unstable or far off. And if we add the polarization, everything improves pretty significantly for the profile and also the parameters. Only the coarse mode remains a problem typically, like this is all the two indexed, like the radius of the coarse mode and the width of the coarse mode are far off. And if we add an Almukanta scan, things improve even further. Green and orange almost always match except for the coarse mode aerosol. And also the trace gas profiles improve quite significantly. This is just another example for different profile shape. It's just interesting to see that we can pretty well resolve, even with the conventional retrieval, elevated aerosol layers. But yeah, also here we get a lot of improvement on aerosol related quantities by introducing polarimetry. So this is the conclusions. Yeah, main take home message is maybe that polarization for in MAX-DOAS introduces 50% more information and about the same amount of accuracy for aerosol related quantities. Well, for trace gas profiles, it's unfortunately pretty low. It's below 20%. And an exception is the coarse mode, aerosol mode, the coarse mode of the aerosol, where we get little information, mostly because we just measure until 500 nanometers and longer wavelength would be required to get better information on that. Yeah, and for the outlook, there are different directions you can go, but I don't want to outline them now in more detail. And rather say, put some acknowledgements here especially to my direct supervisor, Udo Fries and Ulrich Platt, and also to Robert Spur, who was really well supporting me with the radiative transport model. Also my current supervisor, Jochen Stutz at UCLA, who supported this visit here and everything. And a big thanks to all the people that carried me through the PhD madness. Yeah, and with that, I'm done and open for questions. Thanks.
Yeah, any question from the audience?
And then for our online people, because they can hear me right now as well, please put your question in the chat and I'll read it out loud. We'll just take turns.
Thank you. The first, I was a little bit surprised you mentioned that you don't have a truth for the solar spectrum.
Yeah.
Are there no cannot use telescopes in space that are looking at the sun in those wavelength spectra and use those, or?
There are actually, as you say, lots of spectra like this available. But for the MAX-DOAS technique, the attenuations of the gases that we measure are very small, also exceptionally small compared to other techniques. It's on the order of per mil. And so any shifts or instrumental effects, they just make it impossible to do the evaluation. So you have to record the two spectra that you want to evaluate against each other with the same instrument.
Okay. Yeah, I see. And then the second thing is, you mentioned the different, like some confounding effect of multiple paths. Is there, do the numbers work out so that you could tune the number of paths by changing the collimation of the incoming light into the instrument, or not so much?
You mean changing the collimation of the instrument and thereby changing the light path through the
The
atmosphere?
possible light paths, yeah. Does the
Yeah.
numbers work out that works out, or you have? I'm not sure.
Actually, there were thoughts about this, but I think you could do it, but I'm not sure about the actual amount of information that it adds. Or if you can, you mean instead of changing the elevation, just changing the collimation,
divergence,
for
yeah,
instance.
yeah.
I did not test it. Would be interesting maybe if this is an approach. Yeah. And
Well, excellent talk. Thank you so much. What strikes me was the spectral, variability of the polarization, and so actually it's going up with wavelength. And so here it stops at 500 nanometer. So I guess, even beyond 500, there is still polarization. And so we probably need to take some more measurements, and we have a spectrometer that can go up to 2500. And so.
But there's also measurements in the literature.
Yeah, but so the understanding is this polarization is mostly due to Rayleigh scattering, which is in this spectral region. But polarization sensitivity actually is a big topic in remote sensing, because even you go to the thermal infrared, that's still polarization. I think Chris actually did a correction algorithm recently, and thermal infrared. So I think that those are interesting topics, and we can further explore. Yeah. Thank you.
It's okay. Actually, I have one question. So you have the MAX-DOAS, and you have one angle is like elevation angle. Then you have also azimuth angle. And I saw you have this time-dependent like spectrogram of this like color plot of this profile was time. And where's that azimuth angle coming
For this, like the example data, it was towards northwest, and it was fixed.
Oh, fixed. Okay. And for that angle, the second angle, what's used for? Like
typically, either to get some horizontal resolution. So you measure in different directions and perform the vertical profile retrieval, and then you can see differences. And in the context of polarization, it can also be used to optimize the viewing geometry, because ideally you look into direction where the polarization is strong.
Yeah.
Scattering or things like that. But I think the main purpose of it, how it is used, is just get horizontal.
Okay. Thank you. Yeah.
Oh, sorry, and for direct sun observations.
Oh. Okay. Yeah, thank you for the wonderful presentation, and we welcome you to University of Maryland, and we look forward to working with you in this week.
Me
Thank
too.
you. Yeah. Let's thank the speaker again.